Welcome to Science Pills. Look up for a second. Right now, suspended in the invisible air above your head is a freshwater reservoir holding roughly 13,000 trillion liters of water.
Yeah, it's a volume so massive it's honestly hard to conceptualize.
Right, like it could seamlessly hydrate the entire planet. That is, if we could just figure out how to squeeze the sky.
Exactly, and today we're looking at the engineered material that finally does exactly that.
Which is just wild to me. We're investigating a technology that takes the driest, most punishing desert air on Earth and silently turns it into a glass of drinking water. And it does this using nothing but ambient sunlight.
I know, it sounds like an absolute violation of the laws of physics, right?
Yeah.
But the reality is it's peer-reviewed, heavily tested chemistry.
Yeah.
And I mean, it's arriving not a moment too soon, because the ground beneath our feet is telling a very different, much darker story about the future of human survival.
That contrast is really the mission of today's deep dive. We're staring down the central, almost cruel paradox. If you look at a globe, you see a blue planet. It's mostly water.
Right, but institutions like the UN and the World Bank have formally declared that human civilization is entering an era of global water bankruptcy.
Yeah, and the projections are just staggering. By the year 2050, 5 billion people are expected to face severe water stress. 5 billion.
Which is more than half the projected population of the planet.
It's terrifying.
It really is. And the terminology those institutions use is highly deliberate. We should probably define it carefully. Bankruptcy isn't just a dramatic buzzword here.
Right, it's not just PR.
No. In a financial context, bankruptcy means your liabilities have overwhelmingly exceeded your assets, right? To the point where your operational baseline is destroyed. It can't be restored.
So in hydrological terms, it means the exact same thing.
Exactly. Our traditional baselines for groundwater and surface water have been depleted far beyond their natural geological capacity to recharge.
We've basically overdrawn the planetary account, and the bank is calling in the debt.
That's exactly it.
So we have a massive stack of sources to go through today to understand the mechanics of this crisis, and more importantly, the mechanics of the solution.
Yeah, we're pulling from academic journals like Nature, Water, and Science Advances.
Right, plus technical protocols on a highly advanced field called reticular chemistry, and comprehensive reports surrounding the 2025 Nobel Prize in Chemistry.
It's a lot of ground to cover.
It is. But the goal here is to explore how we transition away from our depleted terrestrial water systems and tap into that 13,000 trillion liter atmospheric reservoir using an engineered material known as a metal organic framework, or MOF.
And we really have to look at this through the lens of absolute necessity.
Yeah.
To understand the gravity of the MOF breakthrough, we have to look at the failure cascade of our current systems.
Yeah, because we aren't just projecting a crisis for 2050. It's happening now.
Currently, over 2 billion people, roughly 1/4 of humanity, lacks safely managed drinking water. Furthermore, 703 million people lack access to even basic water services.
I want to translate those statistics into the actual human cost because, the numbers get so large they kind of lose their meaning.
They absolutely do.
According to reports from organizations like water.org highlighted in our research, poor access to safe water and sanitation kills 1 million people around the world every single year.
And the burden of this crisis isn't a flat distribution. It's highly skewed.
Right.
It disproportionately affects women and children in developing regions. The sociological impact is just as devastating as the biological one.
How so?
Well, in many water-stressed regions across sub-Saharan Africa and parts of Asia, the primary logistical responsibility for water retrieval falls squarely on women and young girls.
Oh, wow. So they're the ones doing all the heavy lifting.
Literally, we are talking about millions of people spending hours every single day walking to remote, often contaminated water sources.
Which creates a compounding poverty trap.
It creates an inescapable anchor. I mean, this physical burden causes long-term spinal and pelvic injuries from carrying heavy loads.
Ugh, that's brutal.
And it exposes these women to exceptionally high risks of violence during these isolated long journeys. But fundamentally, it steals time.
Right, time they could be spending elsewhere.
Exactly. When a child spends 6 hours of her day fetching a jerry can of muddy water, she's not sitting in a classroom.
Yeah.
When a woman spends her entire morning securing water for her family, she cannot participate in the local economy. Water poverty is time poverty.
It ensures that entire generations remain economically paralyzed. And our traditional engineering solutions are essentially hitting a geological wall, right?
Yeah, they really are. For the last century, our answer to water scarcity was basically just to drill a deeper hole.
Right, just keep digging.
But the aquifers are drying up, and they're drying up permanently. Look at the Indo-Gangetic Plain in India, or the Ogala Aquifer in the American Midwest.
Those are massive subterranean oceans, right?
Yeah, massive. They took millions of years to fill during previous ice ages. But we're draining them in a matter of decades to feed industrial agriculture.
And when you drain a deep aquifer, you don't just lose the water, do you?
No, you often lose the physical storage space itself. The geology actually collapses in on itself, a process called subsidence.
Wait, the rock actually collapses?
Yeah, the pore spaces in the rock and soil that once held water are crushed by the weight of the earth above them. So even if we stop pumping today, and it rained continuously for 100 years, those aquifers could never refill to their original capacity.
Because the container itself is broken.
Exactly. That is the true meaning of hydrological bankruptcy.
Which brings us to desalination. Because whenever the water crisis is brought up, someone always points to the ocean.
Always.
We have unlimited salt water. We have reverse osmosis plants. So why isn't desalination the ultimate global fix?
Well, desalination is a powerful, necessary technology, but it's bound by severe geographical and thermodynamic limitations.
Makes it.
I mean, if you're a landlocked nation like Chad or Afghanistan, or a rural community sitting 300 miles inland from the coast, a desalination plant on the ocean doesn't help you.
Right, unless you build a multi-billion-dollar, continent-spanning pipeline infrastructure.
Yeah, to pump that heavy water uphill.
Not to mention the environmental and energy costs of all that.
Exactly. Pushing salt water through a reverse osmosis membrane requires massive amounts of electrical pressure. It's incredibly energy intensive.
And there's a byproduct, right?
A massive one. A highly concentrated toxic brine waste. You take the salt out of the water, but you had to put that salt somewhere.
And usually it just goes right back in the water?
Typically, yeah. It's pumped right back into the ocean, where it creates hypersaline dead zones that just suffocate local marine ecosystems.
So desalination works well for wealthy coastal megacities.
Sure, but it is not a decentralized, universal solution for the 5 billion people facing water stress.
Okay, so terrestrial reservoirs are tapped out, aquifers are collapsing, and the ocean is too expensive and corrosive to pump inland.
Right. That leaves us with the alternative reservoir we mentioned at the start, the sky.
The sky.
The Earth's atmosphere contains 13,000 trillion liters of fresh water at any given moment. To visualize that, it's roughly 1/7 of all the water in every single lake and river on the entire planet, just floating invisibly as vapor.
And the defining advantage of the atmospheric reservoir is its decoupling from terrestrial limits.
Meaning it's not tied to the ground.
Exactly. It's constantly naturally recharged by the global solar water cycle. The sun evaporates ocean water, the wind carries it inland, and it hangs in the air.
It's inexhaustible.
It's an inexhaustible, dynamically replenishing reservoir that physically touches every single square inch of the globe, regardless of borders or pipelines.
Okay, let's unpack this. If we are literally swimming in an ocean of invisible fresh water, why aren't we just wringing it out of the air right now?
Well,
I mean, atmospheric water harvesting, or AWH, isn't a new concept. Anyone with a household dehumidifier in a damp basement knows you can pull water from the air.
you plug it into the wall, it hums for a few hours, and you pour out a bucket of water. Why can't we just scale up a dehumidifier and put it in the desert?
Because you immediately run into what engineers call the thermodynamic trap.
The thermodynamic trap. Okay, explain that.
We need to dissect how that household dehumidifier actually works. It relies on vapor compression. It uses chemical refrigerants to chill a set of metal coils.
Right.
As the ambient, moist air gets blown over those cold coils, the temperature of the air drops below its dew point.
So the air can't hold the moisture anymore.
Exactly. The air can no longer hold its moisture as vapor, so it condenses into liquid droplets. It's the exact same physics as a glass of ice water sweating on a hot summer afternoon.
But I'm looking at the thermodynamic data from our sources, and it explicitly states this method completely fails in arid environments.
It does.
It hits a wall when the relative humidity drops below 40%. Walk me through the physics of why cold coils fail in dry air.
It comes down to the dew point curve. Relative humidity is a measure of how much moisture the air currently holds compared to the absolute maximum it could hold at that specific temperature.
Okay.
In a humid basement, the air is nearly saturated. You only have to cool it down by a few degrees to hit the dew point and trigger condensation. That requires a reasonable amount of energy.
But in a desert...
In an arid desert, the air might only hold 15 or 20% of its maximum capacity. The moisture is incredibly sparse.
So you have to work harder to get it out.
Much harder. To force that dry air to release its water, you have to plunge the temperature of massive volumes of air to near freezing levels.
Wow.
The energy required to power the compressors, to chill that much air to that extreme degree, becomes catastrophic.
Give me the numbers. How catastrophic are we talking?
Well, the engineering data shows that in arid conditions, traditional cooling condensation methods require anywhere from 2.78 to a staggering 27.8 kilowatts of energy to produce just 1 single kilogram of water.
That is financial bankruptcy. If you're trying to provide water for a village, you would spend a fortune on electricity.
Yeah, and if you're relying on a local diesel generator or a coal-fired power plant to provide that electricity, the carbon emissions you produce just to run the compressors would drastically worsen the very climate change driving the water scarcity in the first place.
It's a massive net negative. You cannot chill your way out of a water crisis in the desert.
You really can't.
So if we can't use cold, what about chemical sponges?
Yeah.
Like desiccants, the little packets of silica gel that say, do not eat in a new shoebox.
Right, right.
They absorb moisture from the air without needing a power cord. Why can't we fill a giant shipping container with silica gel, open the doors to the desert wind, and then squeeze the water out later?
Desiccants present a different thermodynamic trap. Let's start with silica gel. It relies on a physical process called capillary condensation. It acts like a microscopic sponge. But capillary action is highly inefficient at low humidity. If the air is bone dry, silica gel simply won't pull the water molecules out of the air with any meaningful speed or volume.
It's just too slow.
Yeah, the kinetics are too slow.
What about stronger chemicals, then? The sources mention natural minerals called zeolites.
Zeolites. Zeolites are incredibly aggressive at capturing water. They have a massive chemical affinity for moisture.
So they would work in the desert.
A zeolite will absolutely rip water molecules out of 10% humidity air. It solves the capture problem completely.
But there is a catch.
A massive one. Zeolites capture water by forming very strong, almost covalent-like chemical bonds with the water molecules.
Meaning they don't want to let go.
Exactly. The water gets locked into the mineral structure. To get that water back out, to trigger desorption, you have to supply enough thermal energy to forcefully break those intense chemical bonds.
Meaning you have to heat it up. How hot?
You generally have to heat zeolites to well over 200 degrees Celsius, and sometimes over 300 degrees, to get them to fully release the water they trapped as vapor.
200 degrees Celsius is double the boiling point of water.
Right. And to reach those extreme temperatures, you have to burn concentrated fossil fuels or use intense electrical resistance heating.
Which puts us right back in the same thermodynamic trap as the refrigeration coils.
Exactly. If you need a massive industrial power source to boil the sponge to get a cup of water, it's completely useless for a passive, off-grid system in a remote, impoverished community.
Let's clearly define the barrier here, because this is the crux of the entire technological pursuit. We need a material that is aggressive enough to pull sparse water molecules out of bone-dry desert air, like a zeolite.
Yes.
But it has to hold those water molecules loosely enough that we don't need a blast furnace to get the water back out.
Right. Capture at low humidity and release at low energy.
Which was considered a chemical impossibility for decades.
It was. Until the emergence of reticular chemistry and the work of Professor Omar Yaghi at UC Berkeley, which ultimately won him the 2025 Nobel Prize in Chemistry.
The backstory of Professor Yaghi is vital here, I think, because it frames the entire intent of the technology. We're talking about highly advanced atomic architecture, but the inspiration didn't come from a theoretical desire to win awards.
No, not at all.
The sources note that Yaghi grew up in a refugee community in Jordan.
Yeah, his entire worldview on hydrology was shaped by extreme scarcity. He's spoken in interviews about his childhood, specifically recalling the sensory memory of the local water truck.
The whispers.
Yes, the whispers. The infrastructure in his community didn't include municipal pipes running to individual homes. Water had to be trucked in.
Wow.
And he described how a distinct murmur, a wave of whispers, would ripple through the neighborhood, signaling that the truck was approaching.
And when that whisper hit, it triggered a frantic, desperate rush, right? Every family grabbing plastic jugs, buckets, whatever containers they owned, and physically sprinting to the truck to secure their life-sustaining ration of water before the tank ran dry.
Exactly. When your foundational childhood experience involves your physical survival, depending on whether you can run fast enough to beat your neighbors to a diesel truck, a UN projection about a 2050 water crisis isn't an abstract data point.
It's a terrifying, visceral reality.
Right, and that psychological imprint drove Yaghi's ultimate vision. He didn't just want to build a better municipal filtration plant. He wanted to entirely sever human reliance on the centralized water truck.
He wanted to invent what he termed personalized water.
Yes, the idea that water generation should be as localized and personal as a rooftop solar panel.
And to achieve that, he invented an entirely new class of materials,
Mhm.
metal organic frameworks, or MOFs. Now, metal organic framework sounds highly intimidating, like structural scaffolding for a spacecraft.
It does sound intense.
I want to break down exactly what this is at an atomic level.
Well, the name is actually a highly literal description of the chemistry. MOFs are synthetic, highly porous, crystalline materials. They're built using two distinct components: inorganic metal nodes and organic molecules known as linkers.
So think of a MOF like a microscopic set of tinker toys. The metal nodes are the wooden spools with the holes in them. They act as the structural hubs or joints.
Yeah.
And the organic linkers are the little wooden sticks that plug into the spools to connect them together.
That analogy holds up remarkably well, actually. By strategically selecting which metal you use for the hub and which specific organic molecule you use for the connecting stick, a reticular chemist acts as an atomic architect.
They're building at the atomic level.
Exactly. They can design and synthesize three-dimensional lattices of repeating geometric cages. And because they're building this from the atom up, they can dictate the exact size, shape, and chemical environment of the empty space inside those cages with sub-nanometer precision.
They're building custom-designed molecular traps.
Precisely. And the defining characteristic of a MOF, the reason it is so valuable, is its extreme porosity.
Because it's essentially a rigid framework of mostly empty space.
Right. And because of that, the internal surface area is astronomically high.
The scale provided in the sources is difficult to wrap the mind around.
It really is.
If you take just a few grams of an MOF powder picture, a small spoonful of white dust resting in the palm of your hand, and you were to theoretically unfold every single microscopic cage, flatten out all those internal pore walls and lay them side by side on the ground, how much area would that single spoonful cover?
The internal surface area of just a few grams of a highly porous MOS can equal the square footage of an entire professional football arena.
Wait, really? A football arena of reactive surface area hidden inside a teaspoon of powder?
It's mind-boggling. Which means when you blow air through that powder, the water vapor inside the air isn't just brushing past the exterior of a grain of sand. It's being forced through a sprawling, massive labyrinth of chemical binding sites.
It maximizes the physical contact between the gas and the solid.
Exactly.
But massive surface area alone doesn't solve our thermodynamic trap. We discussed how silica gel also has high surface area, but fails at low humidity.
Right.
What is the specific mechanism that makes a MOF so revolutionary for pulling water out of dry air?
It relies on an adsorption mechanism defined by an S-shaped isotherm.
Okay, I'm going to need a translation on S-shaped.
You go there.
Fair enough.
Yeah.
An isotherm is simply a mathematical curve on a graph that plots how much water a material absorbs as the ambient humidity increases.
Okay.
If you plot a traditional material like silica gel, the curve is somewhat linear or gently sloping. As the humidity slowly goes up, the silica gel slowly soaks up more water. It's a gradual linear relationship.
But an MOF behaves differently.
Very differently. An MOF behaves dynamically. If you look at the isotherm graph for a water harvesting MOF, the line stays completely flat near zero.
Flat, so it's not absorbing anything. Right. As the humidity creeps up, 5%, 10%, 12%, the MOF does absolutely nothing. It remains bone dry. But the material is engineered with a very specific, tunable threshold known as the step pressure.
Okay, let's say the architect tuned the step pressure to exactly 15% relative humidity.
At 14.9%, the MOF rejects water. But the absolute millisecond the ambient air hits that 15% step pressure, the energetics of the system flip.
Like a switch.
Exactly like a switch. The very first water molecules from the air are pulled into the pores and bind to specific primary sites, usually the metal hubs themselves.
They act as molecular anchors.
In chemistry, we call them seeds. Once those first seed molecules form hydrogen bonds with the metal, they alter the chemical environment of the entire pore.
Oh, I see.
They create a highly attractive local field. Suddenly, other water molecules in the air aren't just attracted to the MOF structure, they're aggressively attracted to the seed water molecules.
Because water loves water.
Exactly. It triggers a cascading chain reaction. The water molecules rapidly pull each other into the pore, forming clustered networks.
And on the graph, the line representing water uptake rockets straight up vertically.
Forming the steep middle section of that S shape, the pore fills completely and instantly.
So it isn't a passive sponge. It's a highly sensitive all-or-nothing trap.
That's a great way to put it.
It waits patiently for the exact thermodynamic condition and then violently snaps shut, packing the football arena full of water clusters.
And here is the crucial breakthrough that hacks the energy trap.
Yeah.
The nature of the bonds.
Right.
Because the vast majority of the water molecules are binding to each other via relatively weak hydrogen bonds, rather than forming intense direct chemical bonds with the MOF framework like a zeolite does. They're held loosely.
They're clustered together, but they aren't welded to the walls.
Which means desorption, the release phase, is incredibly easy. You do not need to blast the MOF with 200 degrees of industrial heat to break the water loose.
A mild temperature swing is enough.
Yes. A very mild temperature swing is sufficient to break those weak hydrogen bonds. In fact, merely exposing the MOF to ambient natural sunlight provides enough thermal energy to agitate the water clusters, turn them back into vapor, and release them from the pores.
That's incredible. Zero electrical energy to capture the water, zero electrical energy to release it. You've completely bypassed the thermodynamic and financial bankruptcy of traditional atmospheric harvesting.
And that is exactly why Omar Yaghi won the Nobel Prize.
But the journey from a theoretical Nobel-winning concept to a physical device saving lives in a desert is rarely a straight line.
No, it never is.
The sources track the evolution of this specific application, and it highlights a massive early roadblock. The first prototype material that successfully proved this concept in the field was a framework called MOF 801.
Right. MOF 801 was a monumental proof of concept. It was the first undeniable validation that the S-shaped isotherm could be weaponized against aridity.
They took it to the desert, right?
They did. The researchers took a device using MOF 801 into the Arizona desert. The conditions were harsh. The relative humidity dropped from around 40% at night down to a bone-dry 8% during the peak heat of the day.
And despite dropping to 8% humidity, the MOF 801 successfully pulled water from the air and released it using only sunlight.
Yeah, it proved the physics worked outside the laboratory.
But it contained a fatal economic flaw. MOF 801 utilized zirconium as the primary transition metal for its structural nodes.
Zirconium, yes.
I'm looking at the cost analysis from the sources. Zirconium is a specialized, relatively rare metal. It's incredibly difficult to purify because it's almost always found mixed with hafnium in nature.
Which drives the price way up.
The sources state that the high-grade zirconium required to synthesize MOF 801 cost approximately $160 per kilogram.
Which immediately kills its viability as a global humanitarian solution.
Yeah, you can't build global infrastructure at that price.
Exactly. If your ultimate goal is to build massive shipping container-sized harvesters holding hundreds of kilograms of material to provide water for impoverished rural villages across sub-Saharan Africa, a raw material cost of $160 a kilo means the technology is dead on arrival.
It's a billionaire's novelty, not a global infrastructure replacement.
Right. The team knew they had a materials cost crisis. They had to find a cheaper alternative.
And that pursuit led to the benchmark successor, the absolute game changer in this field, MOF 303.
MOF 303 represents the inflection point where this technology transitioned from academic theory to commercial reality.
What was the fundamental change?
The foundational shift was eliminating the zirconium. MOF 303 swaps out the exotic zirconium nodes for aluminum.
Aluminum. Element 13 on the periodic table.
The very same.
One of the most abundant, heavily mined, and ubiquitous metals on the crust of the Earth. We make soda cans out of it.
And because of that abundance, the cost of the raw metal plummeted. By transitioning to aluminum, the cost of the metal precursor dropped from $160 per kilogram down to roughly $3 per kilogram.
$3. That is a 150-fold reduction in price. That moves it from the realm of aerospace pricing down to standard industrial commodity pricing.
Huge difference.
But here's the massive pushback I have against this, based on standard engineering principles. Whenever you take a highly complex precision machine and you swap out the premium expensive components for the absolute cheapest available alternative, you always pay a penalty in performance.
It's a fair assumption.
A $3 part does not perform as well as a $160 part.
In traditional mechanics, you're correct. But in molecular chemistry, the atomic properties dictate performance, not the price tag. And the data shows that MOF 303, despite being 150 times cheaper, actually performs vastly better than the zirconium model.
Considerably better. The metrics are wild. MOF 303 is lighter, and it holds twice as much water.
Twice as much.
The studies indicate that MOF 303 can capture 0.7 liters of water per kilogram of material at just 10% relative humidity, measured at 27 degrees Celsius.
10% humidity is hyper-arid. It's drier than the average day in the Sahara Desert.
And yet, 1 kilogram of this cheap aluminum powder can aggressively rip nearly 3/4 of a liter of liquid water out of that barren air. Walk me through the physics of that. How does a cheaper metal inherently hold more water?
It comes down to atomic mass and physical volume. Zirconium is a heavy transition metal. It's massive.
Okay.
When you build a molecular cage out of zirconium, the metal hubs themselves take up a significant amount of the physical space and contribute heavily to the total weight of the material. It's bulky scaffolding.
Like framing a house using massive steel I-beams instead of 2x4s, the walls are thick so the rooms inside are smaller.
Exactly. Aluminum is incredibly light and atomically much smaller. When you swap the heavy zirconium for light aluminum, the structural framework itself weighs less, and the metal hubs take up less physical space.
This means the empty pore space, the room inside the cage where the water goes, constitutes a much larger percentage of the material's total volume and weight.
Less metal means more room for water.
But the aluminum hub is only half the architecture. What about the organic linkers connecting them?
The precise chemistry of the linker is what supercharges MOF 303's performance at 10% humidity. For this specific framework, they utilized an organic molecule called 1H-pyrazole 3N5-dicarboxylate. We'll abbreviate it as PZDC.
PZDC. Let's dissect why that specific molecule is magic.
The PZDC linker contains a chemical structure known as a pyrazole ring, which prominently features 2 nitrogen atoms.
Okay, 2 nitrogen atoms.
In the realm of reticular chemistry, those nitrogen atoms act like highly aggressive molecular magnets for water. They create a fiercely hydrophilic or water-loving environment along the walls of the pores.
So the nitrogen atoms are essentially waving flags, chemically screaming at any passing water molecule to stop and attach.
Yes. They dramatically lower the energy barrier for those initial seed water molecules we discussed earlier. The infinite aluminum oxide chains are linked together by these PZDC molecules to create a continuous, one-dimensional pore system.
And the diameter of that pore is engineered to be exactly 0.6 nanometers wide.
Right.
The sources emphasize that 0.6 nanometer dimension heavily. Why is that specific width so vital?
Because it's matched to the physical dimensions of the target molecule. The kinetic diameter of a single water molecule is approximately 0.26 nanometers.
Okay, I want to visualize this. A 0.6 nanometer pore for a 0.26 nanometer molecule. Imagine a long hallway in an office building.
Okay, I'm picturing it.
The hallway is exactly wide enough for 2 people to walk down it shoulder to shoulder, but not an inch wider.
That is a perfect visualization. It's a Goldilocks dimension. If the pore was 2 nanometers wide, like a massive gymnasium, the water molecules floating through the middle wouldn't interact strongly enough with the hydrophilic nitrogen atoms on the walls.
The capture kinetics would be slow.
Right. And if the pore was 0.3 nanometers wide, it would be a single file line. The water molecules would block each other, causing a kinetic traffic jam.
But at exactly 0.6 nanometers, the 2 water molecules can rush into the hallway side by side.
Exactly. They're close enough to the walls to be grabbed by the nitrogen magnets, but they're also forced to be close enough to each other to immediately form those vital hydrogen bonds and cluster together.
It forces rapid interaction without restricting flow,
Which results in incredibly fast sorption kinetics. MOF 303 can fully saturate with water in a fraction of the time it took older materials.
Amazing.
And there's one final critical advantage to the PZDC linker: stability.
Right, because water is known as the universal solvent. If you build a delicate molecular cage and constantly flush it with water, you risk hydrolysis.
Yeah, the water molecules can attack the metal ligand bonds and literally dissolve the framework from the inside out.
The cage just collapses into useless mush.
Which happened frequently with early MOF designs. But the pyrazolates in the PZDC linker form immensely strong coordination bonds with the aluminum metal centers. The architecture is incredibly rigid and resistant to hydrolysis.
So it lasts.
MOF 303 has been tested in laboratories for hundreds of aggressive hydration and dehydration cycles, and the crystal structure does not degrade. It remains intact.
So we have synthesized a material that is phenomenally cheap, structurally bulletproof, and geometrically weaponized to rip water out of 10% humidity air.
That's a huge chemical triumph.
It is. But having a miracle powder in a pristine, climate-controlled laboratory Petri dish is one thing.
Yeah, real life is different.
If this technology is going to save 5 billion people, you have to engineer a physical machine. You have to take this powder out of the safety of the lab and subject it to the most brutal, unforgiving environmental crucible on the planet.
Which brings us to August of 2022 and the ultimate field test detailed in the Nature Water paper. The research team packed up their material and headed into Death Valley National Park.
They didn't just go to Death Valley, they set up their equipment at Furnace Creek.
Yes, Furnace Creek.
For anyone who hasn't studied the geography of the American West, Furnace Creek sits deep below sea level at the very heart of the valley. It currently holds the official global meteorological record for the highest reliably recorded air temperature on Earth.
It's a barren, hostile oven that actively tries to kill anything biological.
And the field data from the study paints a stark picture of just how extreme those conditions were during the test.
The researchers measured the ambient ground temperatures reaching a blistering 60 degrees Celsius.
That translates to 140 degrees Fahrenheit radiating off the soil.
Just insane. But the heat isn't even the hardest part for a water harvester. The true test is the lack of moisture.
Right, the aridity.
Exactly. More critically for atmospheric harvesting, the nighttime relative humidity at Furnace Creek plummeted to as low as 14%.
I want to pause on that. 14% humidity at night. Usually in a desert, the temperature drops at night and the relative humidity spikes, giving you a brief window to collect dew. If the absolute peak moisture you have to work with during the coolest part of the day is 14%, you are quite literally trying to squeeze water from a stone.
And yet, they subjected their device to these conditions without any electrical assistance.
They tested a completely passive physical machine. No power cords, no diesel generators, no moving fans. Zero external energy.
Nothing but the environment.
Let's dissect the engineering of this passive device. Because you cannot just dump a pile of aluminum MOF powder on a folding table in Death Valley and expect a glass of drinking water to magically appear.
No, you definitely cannot.
How was this physical harvester actually constructed?
The device utilized what we can describe as a box-within-a-box passive thermal design. The core of the system is a removable MOF cartridge.
Okay, a cartridge.
The operational cycle is divided into two phases. During the night, the outer box is manually opened. This exposes the internal MOF 303 cartridge directly to the ambient desert air.
The night wind just blows through the box.
Yes. Over the course of the long desert night, the MOF acts as our highly tuned molecular trap, passively absorbing that sparse 14% humidity deep into its engineered pores, locking it in with hydrogen bonds.
Okay, so by dawn, the microscopic football arena is packed full of water molecules. Then what?
When the sun rises, the operator seals the outer box completely shut, creating a sealed internal microenvironment.
Like a little greenhouse.
Exactly. The outer casing is made of transparent or highly conductive materials designed to capture ambient sunlight. As the desert sun beats down, it generates internal heat. This solar-driven heating raises the temperature of the MOF cartridge.
And because the water is only held by weak hydrogen bonds, that mild solar heat is enough to trigger desorption.
Exactly. The thermal energy agitates the clustered water molecules, causing them to break their bonds and explode out of the MOF pores as a dense water vapor.
And since the box is sealed, it rapidly spikes the relative humidity inside to near 100%.
Yes. You essentially create a localized, artificial, high-humidity rain cloud trapped inside the box.
So cool. And the final step is collection.
Right. The external walls of the outer box, or the condenser unit, are shielded from direct sunlight by reflective shades. Because they're shielded, they remain significantly cooler than the superheated vapor inside.
So when that dense, high-humidity vapor hits the cooler condenser walls, it hits its localized dew point.
Yes, it condenses into liquid water droplets and gravity pulls it down into a collection vessel at the bottom.
But I'm looking at the physics of this design and I see a massive structural contradiction.
Oh, what's that?
You noted earlier that MOFs are incredibly porous, low-density powders.
Right.
In thermodynamics, porous powders are terrible conductors of heat. They're highly effective thermal insulators.
Yes. You've identified the primary engineering bottleneck. The thermal conductivity of a bulk MOF powder is typically abysmal, often measuring less than 2 watts per meter Kelvin.
To put that in perspective, copper has a thermal conductivity of around 400.
Right, big difference.
So if you just fill a thick tray with MOF powder and the sun's heat hits the top of the pile, only the very top layer of powder is going to get hot enough to release its water.
Yes, the powder buried deep inside the pile will be completely insulated.
It'll stay cool and the water trapped inside it will never be released. How do you force solely heat to penetrate a thermal insulator?
This specific heat transfer problem was the focus of the PhD thesis of Xiling Zhang, one of the brilliant lead researchers on the project.
Okay. What was his solution?
The team realized that they had to mathematically optimize the volume to surface area ratio, or the VSR. If you have a thick, dense bed of powder, the ambient air cannot penetrate deeply during the night to deliver the moisture, and the solar heat cannot distribute deeply during the day to extract it.
So how did they rebuild the cartridge to solve both the airflow and the heat flow problems simultaneously?
They moved away from using loose powder entirely and engineered a highly complex composite structure. First, they took the MOF 303 powder and subjected it to intense mechanical pressure, pressing it into extremely thin, solid, disc-shaped pellets. Each pellet was about 38 millimeters in diameter, but crucially, only 0.8 millimeters thick.
Less than a millimeter thick, like a fragile microscopic pancake.
Exactly. By making the MOF layer that thin, they guaranteed that heat from the surface could easily penetrate all the way through the material.
But you can't just stack thousands of these pancakes on top of each other, or you end up right back where you started with a solid block of insulator.
Right, so they interspersed the MOF pellets with alternating discs of highly porous nickel foam.
Nickel foam?
Yes, the nickel foam discs were slightly thicker, cut to about 1.5 millimeters. So the final cartridge looked like a towering metallic club sandwich. Nickel foam, MOF pellet, nickel foam, MOF pellet.
Why specifically nickel foam?
It served two vital contrasting functions. First, the nickel foam they used possessed a porosity of over 97%. It was almost entirely empty space.
Wow, 97%.
This meant that during the night phase, the ambient desert wind could easily flow laterally right through the foam layers, carrying moisture directly across the exposed, massive surface area of every single thin MOF pellet.
It created an unobstructed air highway.
Yes. The team calculated it maintained a mathematically perfect volume-to-surface area ratio of 2.6.
And the second function, the heat problem.
Nickel is an excellent thermal conductor. Its thermal conductivity is around 90 watts per meter Kelvin. The nickel foam structure essentially acted as an integrated, three-dimensional heat distribution network.
So when the morning sun heated the exterior of the cartridge, the nickel structural lattice rapidly conducted that thermal energy deep into the center of the stack.
The nickel foam acted like a radiator, warming every single thin MOF pellet evenly and simultaneously from all sides, completely bypassing the insulating nature of the powder.
It's an incredibly elegant, purely structural intervention. You solve the chemical limitations of the material using physical engineering.
Exactly.
So what were the final, verified results of this highly engineered composite cartridge operating in the 60-degree, 14% humidity crucible of furnace-crete?
The productivity metrics were unprecedented for an entirely passive system. Using zero electrical input, relying exclusively on the natural thermal swing of the desert, this device produced up to 285 grams of liquid water per kilogram of MOF per day.
More than a quarter liter of water pulled from the driest air on Earth using only sunlight.
And the researchers pushed it further. They noted that the final bottleneck wasn't the MOF releasing the vapor, it was getting the vapor to condense quickly on the box walls.
Right.
By applying a specialized microscopic hydrophobic coating to the condenser walls, a coating that repels water, they forced the vapor to form droplets and roll down into the collector much faster.
Oh, that's smart.
Yeah, and with this enhancement, they achieved a productivity rate of 200 grams of water per square meter of physical footprint per day.
Which means
it was 3 times more efficient than any previous passive design ever tested.
So, we have proven the science. The material is fundamentally cheap. The physical engineering successfully overcomes the environmental extremes of Death Valley.
Yes.
But there is a massive, often overlooked chasm between a successful academic field test and actually deploying a technology to save 5 billion people.
Oh, absolutely.
We have to manufacture this material, not in tiny glass beakers, but in millions of metric tons.
And that introduces one of the most significant bottlenecks in advanced materials science. Synthesizing highly ordered, complex crystalline frameworks like a MOF in a controlled laboratory is a meticulous process. Scaling that precise atomic architecture up to massive industrial manufacturing is a completely different discipline.
Right. Our sources from Nature Protocols outline a dark irony regarding how early MOFs were traditionally manufactured. It isn't just difficult to scale, it's chemically hazardous.
Yes, very much so. The traditional method used to create early batches of MOFs is known as solvothermal synthesis. To get the organic linkers and the metal nodes to interact and crystallize correctly, chemists often had to dissolve them in highly volatile, highly toxic organic solvents.
Sisa.
One of the most common was dimethylformamide, or DMF.
DMF is a known occupational hazard, right? It's highly toxic to the liver.
Not only is it toxic, but the traditional solvothermal process also typically required high-pressure vessels and incredibly long reaction times, sometimes heating the toxic mixture for up to 24 hours just to yield a tiny amount of powder.
This presents a massive ethical and environmental contradiction. I mean, if your ultimate humanitarian goal is to create a technology that provides clean, safe, life-saving drinking water to the global poor, you cannot base the manufacturing process on millions of gallons of toxic, carcinogenic chemical solvents that ultimately have to be disposed of.
You're just trading a water crisis for a toxic waste crisis.
Exactly. Industrial scalability demands environmental sustainability. The solution cannot be an artisanal lab curiosity. It must be cleanly manufacturable.
And the team behind MOF 303 recognized this immediately.
So how did they crack the mass production bottleneck? How do you build an atomic lattice without the toxic soup?
They developed what is outlined in the literature as a green synthesis protocol, specifically tailored for MOF 303. This was arguably just as important a breakthrough as the material itself.
What did they use instead of DMF?
They entirely abandoned toxic solvothermal methods and transitioned to a simple water-based reflux method.
A water-based method, meaning they just use regular water as the chemical solvent to build the material.
Exactly. The chemistry was optimized to be astonishingly clean. The entire ingredient list consists of just 4 things. Water, a standard, specifically sodium hydroxide, which is common household, like an aluminum salt, like aluminum chloride, and the PZDC organic linker.
No DMF, no exotic organic solvents.
None. The process is remarkably straightforward. The solid PZDC linker and the sodium hydroxide are dissolved together in a large vat of standard deionized water.
Okay.
Then the aluminum chloride, which is also dissolved in water, is slowly poured into the vat while the mixture is mechanically stirred. The entire solution is then heated to a reflux.
Let's quickly define reflux for the listener.
Reflux simply means boiling the liquid, but capturing the steam in a vertical condenser so it cools and drips back down into the vat.
Okay, so you don't lose the liquid.
Exactly. It allows you to maintain the reaction at exactly 100 degrees Celsius, the boiling point of water, without losing any of your solvent to evaporation. They hold it at a reflux for a few hours.
You know what happens in the vat?
As the reaction progresses, the MOF 303 spontaneously crystallizes and precipitates out of the water as a solid white powder. You then simply filter the powder out, wash it with a bit more clean water and a touch of ethanol to remove unreacted salts, and dry it.
It sounds fundamentally like brewing a massive, slightly complex batch of tea.
The simplicity is its power. And more importantly, it is violently efficient.
Meaning a high yield.
Right. In chemical manufacturing, efficiency is measured by yield. How much of your raw ingredients actually become the final product versus how much is wasted. By carefully tweaking the ratio of the sodium hydroxide base, the researchers increased the yield of the reaction from an initial 38% using older, dirtier methods, up to a massive 91 to 94% yield.
Meaning nearly every single atom of aluminum and organic linker put into the vat successfully locks into the crystal structure. There's almost zero chemical waste.
Yes, and they successfully proved the industrial scalability of this green protocol. They moved from tiny 10-milliliter lab flasks up to massive 200-liter industrial vats, comfortably producing 3.5 kilogram batches of MOF in a single run.
The technical metric cited in the papers here is something called the space-time yield. Explain what that measures and why industrial engineers care about it.
Space-time yield is the ultimate metric of factory efficiency. It measures exactly how many kilograms of final product you can produce per cubic meter of your reactor vat per day.
So a high space-time yield means you can produce a massive amount of material using relatively small equipment in a short amount of time.
Exactly, which drastically lowers capital costs.
Right.
The water-based green synthesis for MOF 303 achieved an incredible space-time yield of between 179.5 and 305 kilograms per cubic meter per day.
That is the textbook definition of industrial viability. But the sources also briefly mention an alternative synthesis method that is even more radical, one that doesn't even use water.
Yes. You're referring to mechanochemical synthesis, specifically a process called ball milling.
Ball milling.
Yes, this is a fascinating avenue of green chemistry. Instead of dissolving the ingredients in any liquid solvent, water, or otherwise, you place the completely dry raw materials, the aluminum salt and the linker, into a heavy mechanical mill loaded with solid metal balls.
And you turn it on and just violently smash the powders together.
Essentially, yes. The intense mechanical kinetic energy of the metal balls violently grinding the precursor powders together forces the chemical reaction to occur in the solid state.
So the physical force drives the atoms into the MOF crystal lattice.
Precisely. The entire process takes only minutes to a few hours, completely eliminates the need for solvents, and still yields a highly porous, functional structure.
Wow.
The sources note that a ball-milled MOF 303 achieved a specific surface area of 1,180 square meters per gram.
That is phenomenal. So whether you use massive vats of boiling water or mechanical crushers, the bottleneck of toxic, slow manufacturing has been permanently shattered.
It has.
But I want to introduce another layer to this discovery process based on the broader context of how this field is accelerating. How do chemists actually find these materials? There are millions of possible organic linkers in existence. How did they know that PZDC was the magical Goldilocks molecule to pair with aluminum?
Well, historically, materials discovery was a process of educated trial and error.
Right.
A chemist would spend months synthesizing a new variation, testing it, realizing the pore was a fraction of a nanometer too small, and starting over.
That sounds exhausting.
It was. But that paradigm is shifting rapidly due to the integration of artificial intelligence and machine learning into reticular chemistry.
How exactly does AI predict a molecular cage?
Researchers are now training deep learning models on vast databases of known chemical properties, atomic radii, and binding energies. Before a chemist ever puts on a lab coat or mixes a single drop of chemicals, the AI can digitally simulate millions of theoretical MOF structures.
It's testing them virtually.
Exactly. It can calculate exactly how a specific aluminum node will bond with thousands of different organic linkers.
It's performing digital alchemy.
It acts as an incredibly powerful filter. The AI can virtually test the thermodynamics. It can say, if you build an MOF using this specific linker, the pore size will be exactly 0.55 nanometers, and the nitrogen atoms will be positioned at the precise angle required to trigger water absorption at exactly 12% humidity.
That drastically accelerates the discovery pipeline.
It really does, allowing researchers to pinpoint the absolute optimal chemical combinations like MOF 303 in a fraction of the time.
So the material is structurally perfected, cheap, green to manufacture, and aggressively optimized by AI. The lab phase is officially over. Where is this technology living right now? How is it stepping out of the academic journals and into the physical world?
This is where we are seeing the rapid transition to major institutional and commercial deployment. And one of the most aggressive early adopters and funders of this technology, perhaps unsurprisingly, is the military.
Yeah, the sources detail a specific initiative by DARPA, the Defense Advanced Research Projects Agency. They funded a massive project called Air-to-Water. Walk me through why the military cares so deeply about atmospheric water harvesting.
It comes down to the brutal realities of logistics. Supplying potable water to combat troops deployed in remote, hostile, or arid environments is one of the military's most glaring strategic vulnerabilities.
Because a soldier requires gallons of water a day to survive and operate in the desert heat.
Right. And currently, that water has to be delivered via massive convoys of diesel trucks.
The tether.
Exactly.
Yeah.
Every forward operating base is tethered to a water supply line. Those convoys are slow, they're incredibly expensive to operate, and most critically, they're highly predictable, soft targets for ambushes or improvised explosive devices.
Protecting water convoys requires massive manpower and inevitably costs lives.
Yeah, the fully burdened cost of delivering a single gallon of water to an isolated base in a combat zone can run into the hundreds of dollars.
So if you can eliminate the water convoy, you eliminate the tether, you sever a massive strategic weakness.
Which was the exact mandate of DARPA's Air-to-Water project. They tasked engineering firms with scaling the MOF technology into a deployable, ruggedized tactical unit. They moved beyond the passive solar box used in Death Valley and developed an active refrigerator-sized system utilizing MOS 303.
How does the active system differ?
Instead of waiting for the slow, natural day-night cycle, an active system uses a compact, high-efficiency fuel source or generator to drive forced air through the MOF and then actively heats it to force rapid absorption.
So they're artificially speeding up the cycle.
Right, because they are driving the thermodynamics mechanically. The machine can run multiple complete capture and release cycles every single day, dramatically multiplying the output.
The output goal DARPA set was ambitious, wasn't it?
Very. The target was a unit, liftable by a 4-person team, capable of providing enough completely pure distilled potable water to sustain a reinforced company of roughly 150 troops continuously, 247, pulling from the ambient air.
And it worked.
The technology passed rigorous, independent verification testing at the Aberdeen Proving Ground, proving its mechanical reliability even in environments saturated with outdoor dust and chemical contaminants.
That is a massive real-world validation of the technology under extreme duress, but what about the civilian sector?
Right, that's the big question.
I mean, military contracts are great for funding research, but
Yeah.
we are talking about 5 billion civilians facing water stress. Are there commercial entities driving this into the public market?
Absolutely. The commercialization is accelerating aggressively. Professor Yagi himself founded a company called Atoko, specifically to commercialize these atomic precision materials and transition them to mass manufacturing.
And they aren't the only ones.
No, they're part of a growing ecosystem of startups actively entering this space, including companies like Waha and AirJoule LLC.
The sources mention that these startups are moving far beyond the small passive boxes. They're building units the size of standard shipping containers.
Yes, the scaling up is extraordinary. These larger, active commercial systems are designed to generate up to 1,000 liters of clean drinking water every single day.
1,000 liters. That's enough to sustain hundreds of people, provide hydration for a school, or act as the primary water source for a remote medical clinic.
Exactly. And these container units can be deployed anywhere. They're developing a two-pronged approach. First, they are deploying fully passive or highly efficient solar-powered off-grid systems designed specifically for remote communities, disaster relief zones, or rural agriculture where municipal infrastructure simply doesn't exist.
And the second approach.
Second, they're developing larger on-grid systems for municipal or industrial use. These systems integrate into existing electrical grids, but because of the hacked thermodynamics of MOF 303, they consume a fraction of the electrical energy required by traditional refrigeration-based dehumidifiers or desalination plants.
I want to translate this massive infrastructure discussion down to the individual. For the person listening to us right now who might be sitting in an apartment in a drought-stricken city under strict water rationing, or looking at a dropping well level on a rural property.
Yeah.
What does this mean for them? Is this technology just going to be locked away for military bases and massive desert research projects, or is this physically coming to our backyards?
This brings us back to the culmination of Professor Yagi's vision. The ultimate endgame is entirely aimed at the individual consumer, the realization of the era of personalized water.
Let's dissect that concept of personalized water. What does that actually look like in practice?
Well, the best way to understand it is to look at the historical trajectory of the electrical grid. For a century, electricity was an exclusively centralized resource. Massive centralized power plants burned coal or split atoms, generated massive amounts of power, and transmitted it over hundreds of miles of highly fragile grid infrastructure wires and transformers to reach your house.
Right, and if a tree fell on a wire 50 miles away, or the central plant failed, you were plunged into the dark. You had zero control over your own power security.
But then photovoltaic technology's solar panels became cheap and efficient.
Exactly. And suddenly the paradigm shifted. You could bolt a panel to your roof and harvest ambient solar energy directly from the sky.
You generated your own off-grid power. You decentralized your energy security, cutting the cord to the vulnerable central plant.
And Yagi envisions that exact same decentralization paradigm shift applied to hydrology.
Currently, humanity relies almost entirely on hyper-centralized water infrastructure. We rely on massive, depleted municipal reservoirs, continent-spanning concrete aqueducts, massive chemical treatment plants, and millions of miles of aging, often lead-contaminated underground pipes.
And if the reservoir runs dry due to drought, or the pipe under your street breaks, your home has no water. You're entirely dependent on the centralized system.
But with a commercialized MOF water harvester,
Things change.
with the commercial MOF harvester, we utterly decentralize the water supply. Within the near future, households in water-stressed regions will have appliances sitting in their backyards or on their roofs.
Appliances that run purely on ambient solar heat or draw a minimal amount of power from a standard outlet or a home battery.
Yes, and every single day, they will silently pull the daily drinking, cooking, and sanitation water required for a family directly out of the ambient air.
You completely sever your physical reliance on the municipal pipe.
You achieve personalized, localized, impenetrable water security. You're drawing your daily lifeblood from a dynamically replenishing 13,000 trillion liter atmospheric reservoir that is accessible from literally any GPS coordinate on the planet.
That is a profound, earth-shattering paradigm shift. It takes the fundamental power of biological survival and hands it directly to the individual.
It's the ultimate democratization of the most vital resource on Earth.
All right, let's take a breath and briefly recap the incredible scientific arc we have covered in this deep dive.
We covered a lot of ground today.
We really did. We started with the terrifying reality of global water bankruptcy, a planet rapidly running dry, with historical baselines structurally shattered and billions of human beings staring down the barrel of severe water stress.
We explored the cruel thermodynamic trap of traditional dehumidification that kept the massive atmospheric reservoir frustratingly out of reach.
We then delved into the atomic-level engineering of reticular chemistry. We saw how Professor Yagi's Nobel-winning work created metal-organic frameworks.
And specifically how the aluminum-based MOF 303 utilizes precise 0.6 nanometer physical geometry and hydrophilic pyrazole linkers to actively rip water molecules from hyper-arid air at a fraction of the cost of early zirconium prototypes.
We tracked the technology through the brutal 60 degrees Celsius, 14% humidity test rounds of Death Valley. We saw how physical engineering stacking microscopic MOF pellets with thermally conductive nickel foam solved the heat distribution problem,
proving a passive box could pull water using only the sun. We examined the crucial industrial leap into green manufacturing, proving this miracle powder can be mass-produced safely, cheaply, and without toxic solvents in massive water vats.
And finally, we looked at the commercial reality that is arriving right now, from DARPA utilizing the technology to cut military supply tethers to startups building 1,000-liter shipping container systems,
leading us relentlessly toward a future where off-grid, personalized water appliances sit in our own backyards.
The 13,000 trillion liters of fresh water floating invisibly above your head is no longer out of reach.
The era of localized, personalized water security is arriving.
It's a stunning, undeniable victory of human chemical ingenuity over a seemingly insurmountable global crisis. But before we wrap up, I want to leave you with one final, mind-expanding concept to ponder regarding the ripple effects of this technology.
Yeah, let's look at the big picture.
If we look back at the entire sweeping arc of human history, human civilization itself has been almost entirely dictated by a single, unyielding geographical constraint: proximity to fresh surface water.
Every major historical city, every ancient empire, every modern geopolitical border has been drawn based on access to rivers, natural lakes, and coastal ports. From the Nile to the Tigris, you simply cannot build a thriving city where there is no water.
Until now. If a shipping container packed with engineered aluminum powder can autonomously generate 1,000 liters of pure water a day from the sky, anywhere on Earth, even in the dead center of the Sahara Desert, or the most isolated, driest plateaus of the American West, completely disconnected from any natural river or subterranean aquifer, how will off-grid atmospheric water harvesting redraw the map of human settlement?
If geography is no longer destiny when it comes to human survival, how will this invisible revolution shift geopolitical power and alter exactly where humanity chooses to live in the 21st century?
It's a profound, paradigm-breaking question. When the fundamental rules of our resource landscape change this drastically, the boundaries of human potential expand into entirely uncharted, previously uninhabitable territories.
And suddenly those diagnostic muddy waters we talked about at the very beginning, they don't seem quite so murky anymore.
Sometimes the solution isn't found by frantically trying to fix the old, broken system. Sometimes the solution is found by looking up at the sky, zooming into the atomic level, and building a better trap.
Yeah.